Today we will start group theory. Let's see what is abstract algebra. In this abstract algebra, this is a very huge field. Let me tell you, it's like mathematics is a very huge field. In mathematics, discrete mathematics is a small part. Like in mathematics, calculus is a small part. Okay, so that's the idea. This abstract algebra is a huge field. In this abstract algebra, particularly in our GATE syllabus, we have group theory. Okay, so what we need to study first, we need to see what is abstract algebra. If someone asks you what is abstract algebra, then how can you explain this? Okay, in this abstract algebra, which is a very huge field, in this abstract algebra, basically we will study only group theory. So in this this group theory is in our GATE syllabus. Okay, so let's see first we will start with the introduction to abstract algebra. So what is this abstract algebra? Before I ask you this, can you tell me what is algebra? In your school life you have studied this algebra many times. You have heard this name algebra. So what is the meaning of this algebra? Can anyone tell me what is the definition of algebra? Anyone? Like, what do you think, what comes to your mind when you hear this word algebra? What will come to your mind? Some variables, equations, something, right? Okay, so these things will come to your mind. In your, okay, to your mind x y z will come, some equations will come, some polynomials will come. Correct. Okay, so some polynomials will come, some plus minus will come. Okay, so and so on. So these things will come to your mind when you, okay, when this word, you see this word algebra. Now what is abstract algebra? Okay, so now we need to study the concept of abstract algebra. So what is this abstract algebra? What is this one? Okay, so what is the meaning of this abstract? If you understand this, the meaning of this word abstract, then okay, then you can very easily understand what is abstract algebra. So what is this abstract? What is the meaning of abstract? So let's see that. And this is very interesting. See, okay, just focus here. What is the meaning of abstract? So now let's see. Do you remember? Okay, with example, I'm going to explain you the concept of abstract with example. So do you remember what is Boolean algebra? Can I say this hash diagram is a Boolean algebra? Tell me. This hash diagram. Can I say this is your hash diagram? Can I say this hash diagram is Boolean algebra? See, you don't have to worry if you have not studied what is hash diagram. Okay, if you have not studied set theory, if you have not studied latest Boolean algebra, these things, if you did not study so far, okay, then you don't have to worry, because I'm just trying to explain this concept of abstract. This concept I want to explain, and that is the reason I'm taking this example. But remember, in group theory, we don't study this. Okay, so you don't have to worry. Just wait. When we start group theory, then everything will be clear. No prerequisite is required. Okay, you don't need any previous knowledge in this class. Okay, but to explain this concept, I am taking this example. So this hash diagram, this is a Boolean lattice, right? Correct. So this hash diagram is a Boolean lattice. You know that this hash diagram is a Boolean lattice. Boolean lattice, or I can say this is Boolean algebra. Now tell me, if this is Boolean algebra, then what are the properties of this? What are the properties of this? If this is Boolean algebra, then what are the properties that this will have? For example, if I give you a b c d, now you know that this hash diagram is Boolean algebra, a b c d. Now what are the properties that this Boolean algebra will have? So for example, these properties this will have, like distributive, this property will be there. Okay, I can say commutative, this property will be there. Complement property will be there. De Morgan property will be there. Correct. Absorption property will be there. Absorption property will be there. Idempotence property will be there. Idempotence. Identity property will be there. Right? Yes or no? So basically these properties will be there, if you notice. Okay. Now, so whenever you see this word, whenever I tell you this word, then automatically in your mind these properties will come, right? Agree? Okay, so for example, if I give you this structure, if I give you this structure, then these properties will come to your mind. Now remember, what are ABCD? Can anyone tell me what are ABCD? What is this ABCD? What is this? What is this? So basically here, this ABCD, these are the abstract things. Now let's take okay, so here you can notice these are the abstract things. These can be anything. Basically, let's see a concrete example. So let's see this concrete example, like power set of a comma b. or I can say power set of 1 comma 2 subset. What will be the hash diagram for this? Let's see this one. What will be the hash diagram for this? So hash diagram for this will be phi. You have phi will be related to 1. Okay, this will be related to 2, and this will be related to 1 comma 2. Now you can notice this will be the hash diagram. Can I say this is Boolean algebra? So this is an example from set theory. I am talking for, okay, I am talking about set theory. This is example from set theory. I am taking this set. This is the power set of 1 comma 2. Now, is this a Boolean algebra? Right? You know that this is a Boolean algebra. Why this is a Boolean algebra? Why this is a Boolean algebra? Because this has the same structure as this. They have the same structure. I can say because they have same structure. This and this, they have same structure. And because they have same structure, so I can say this is a Boolean algebra. And as soon as I tell you that this is Boolean algebra, what will come to your mind? All these properties will come to your mind, right? All these properties will be satisfied by this, I can say. So because this is Boolean algebra, so this structure will satisfy all the properties. Now you can notice very simple one thing. Okay, very interesting thing you should notice. Remember, we studied this, we have seen this, and we know that this is a Boolean algebra and this will satisfy these properties. Now you can notice that any structure that will have the same structure as this, okay, anything that will have same structure as this, that will also satisfy these properties. So I don't have to study this separately, right? I don't have to study the properties of this structure separately, because I can immediately, I can say what are the properties that will satisfy. Okay, I know that associative property will be satisfied. I know commutative property will be satisfied. I know distributive property will be satisfied. I know De Morgan property will be satisfied, and so on. So that's the idea. Now, this example I have taken from state theory. Another example I can take from number theory. Let me take this number theory example. Now, let's assume you are studying number theory. In number theory, I give you this set. Okay, 1, 2, 3, 6. This set I give, and this is the operation divisibility. Now tell me, which properties this will satisfy? If I ask you what are the properties that this structure will satisfy, so this is a structure, you know, this is a structure, which properties this structure will have? So again, you can notice that if you make the hash diagram, 1 divides 2, 1 divides 3, and 2 divides 3, 2 divides 6, 3 divides 6. So again, this is a Boolean algebra. Again, you know that this is a Boolean algebra. Why? Because this has the same structure as, okay, this has the same structure. This has the same structure as this. So I can say this is a Boolean algebra. And again, if I ask you what are the properties that will be satisfied by this, then what will you say? Then what will you say? All those properties, right? All the properties that this will satisfy, all those properties this also will satisfy. So I don't have to study this, right? Yes or no? I don't have to spend my time on this. I can directly say that because this has the same structure as this, so I can say this is Boolean algebra, and because it is Boolean algebra, so I can say that it will have all those properties: commutative, distributive, De Morgan, all those properties will be there. Now you can notice one thing. I have given you two examples from different fields. Like this is number theory. This is the example from number theory. This is the example from set theory. Here we have set, here we have numbers, but these are completely different fields, right? Yes or no? Set is completely different thing, and number theory, numbers are completely different things, but you can notice that they have some similarity. Yes or no? So I can say that this structure and this structure, they have similarity. And what is that similarity? They both are Boolean algebra. And because they both are Boolean algebra, so I can say that all these properties will be satisfied. Right? Yes or no? Now, another field I can take another completely different field, that is propositional logic field. I can take propositional logic field. So in the propositional logic field also, let me take this example. Let me take, okay, false, true, some propositional variable p and its negation. Okay, and the relation that I am defining, that is implication is tautology. This is the relation. Implication is a tautology. Okay, can you create the hash diagram for this? See, you don't have to worry if you have not studied propositional logic or set theory. If you did not study Boolean algebra so far, okay, don't worry. this is just for explaining the concept of abstract algebra. This is just for explaining the concept of abstract. Okay, so without knowing all these things, you can very easily understand what is the concept of abstract. Okay, once we start group theory, everything will be clear. Okay, no prerequisite will be required. Okay, so tell me, what will be the hash diagram for this? False, true, p comma, negation, p. Okay, and this is the relation is implication is tautology. Implication is tautology. So tell me, who will who will be the least element? Can anyone tell me? We have already seen the Boolean algebra, we have already seen lattice. So what will be the hash diagram? Who will be the least element? False will imply anything, right? Yes or no? False will imply everything. False will imply everything. So I can say, because you know that false implies anything, this is a tautology. This is a tautology. False implies anything, this is a tautology. So I can say false will imply everything. False will imply p. Okay, can I say p will imply p bar? Can I say this is this tautology? Is this tautology? Is this tautology? Is this tautology? Okay, both are not tautology. Both are not a tautology. So because they are not tautology, so they are not comparable, right? I can say p comma, I can say p comma, these are not comparable. I can say these are not comparable, right? So okay, and you know that everything will imply true. So now tell me, if I ask you what are the properties of this structure? This structure you have, what are the properties of this structure? Can anyone tell me? Do you need to spend some time, like do you have to spend half an hour, 1 hour to study the properties of this? No, because it is also Boolean algebra. This has the same structure as Boolean algebra. They have same structure. So I can say this is also Boolean algebra. This structure is also Boolean algebra. And because this structure is also Boolean algebra, so this also has all those properties: distributive, commutative, De Morgan law, absorption, idempotence, identity, all those properties are there. Okay, so one interesting thing you should notice, that we have seen three different fields. This is example from propositional logic, this is example from number theory, this is example from set theory, and you can notice these are completely different things, but they have similarity. They have same structure. They have same structure as Boolean algebra. All of them are Boolean algebra. So that's the reason I can say that. So tell me, if you want to study the properties of this, or properties of this, or properties of this, then what you should do to save some time? What you should do? Will you study all of them differently? Tell me, will you study this differently, this differently? Will you study that? No. What will you do? Okay, what will you do? Just study Boolean algebra. Just study this abstract thing. This abstract thing you study. See, this abstract thing you study. This thing you study. A, B, C, D. So this you study. You study this Boolean algebra. What you do? Just study the properties of this structure. Only study this abstract template. Yes, very good. Excellent. So this is the abstract template, I can say. Okay, so I can say that this Boolean algebra is an abstract concept. Remember, this is abstract concept, right? Yes or no? So this Boolean algebra is abstract concept. This is an abstract concept. So just study Boolean algebra. And once you study Boolean algebra, then you know that some properties will be there. You know that this Boolean algebra will satisfy some properties. Okay, you already know all these properties will be there. So just study this abstract concept, which is Boolean algebra. Once you study this Boolean algebra, you don't have to study this. You don't have to study this. You don't have to study this. Very simple. So this abstract concept we will study. I can say we should study. Agree? Yes or no? So this is the abstract concept. This Boolean algebra, this is an abstract concept. So I can finally say what is abstract. Like, and tell me one more thing. Okay, one more interesting thing I want to ask. See here, if I ask you, if you study this abstract concept, when you study this abstract concept, then what terms you will use to study this? This is abstract. You already know this is abstract. Okay, because we don't know what is ABCD. Now here, what terms will you use? You will use these words, LUB, right? This word you will use, GLB. You will use this word. These words you will use, correct? You are going to use these words, right? Okay, minimal, minimum, like these words you will use, right? So I can say LUB, GLB, these words you are going to use. Now tell me, if I study this one, okay, now I am studying this one. This is structure I am studying 1, 2, 3, 6. If I study this structure, then what words you will use? In this structure, what words you will use? For this LUB will change its name. You can notice one thing. This LUB will change its name. What is now LUB? In for this structure, what is LUB? For abstract structure, we use this word LUB, GLB. This word we use. Now, for this structure, this LUB will become LCM for this structure. For this structure, LUB will become LCM, because if I ask you what is LUB of 3, 2, if I ask you what is LUB of 3, 2, then that simply means I am asking you LCM of 2, 3 or 3, 2, right? And that will be 6. So, okay, are you getting this point? So this is abstract structure. Here we use the word LUB, GLB, but this is a specific structure. This is some specific structure, right? Okay, here this LUB will become LCM and this GLB will become GCD. If I ask you what is GLB of 2, 1, then what that will become? That will simply become GCD of 2, 1, and GCD of 2, 1 is 1. So idea is very simple. This is abstract and this is specific. In specific, this word LCM, so this LUB will become LCM and this GLB will become GCD. Tell me one thing. This LUB has changed its name. Like, so this LUB is an abstract concept. This is also abstract concept. This LUB, GLB, these are also abstract concept because they are changing their name according to the structure. In this structure, they are LCM, GCD. In the next structure, what they will become? For example, if I give you this structure, okay, let's assume I give you this structure 1, 2, 1, 2. If I give you this structure, then what will be LCM? Sorry, what will be LUB? Now this LUB will change its name. Now LUB will be the union, and now GLB will be the intersection. So you can notice that they are changing their name. This LUB, GLB, these are abstract concept, and because they are abstract, so they are changing their name according to the specific concept. This is a specific structure. This structure is specific, and this is abstract structure. Right? Yes or no? The same idea you can do. The same thing you can do here. Like, okay, if I give you this structure, instead of this structure, let me give you this complete, this propositional logic structure. Let me give you false, a bar, and true. Now tell me, this is a specific structure from propositional logic. Now this LUB will change its name. Now what is LUB? Can anyone tell me? In this structure, what is LUB? LUB is basically the or. LUB is or, and GLB is basically the and, the conjunction. LUB is basically the disjunction. If you notice, LUB is disjunction, and this is a conjunction. And this is a conjunction. Okay, so that's it. So tell me one thing. This union, does it change its name? The name of union, will it change anywhere? Will it ever change its name? Union. This union will never change its name. This intersection will never change its name. But this LUB is changing its name, right? So this LUB is changing. For this structure, the LUB is becoming union. For this structure, LUB is becoming disjunction, right? Yes or no? So now you can notice one thing, that what are the abstract concepts? So what are the abstract concepts? So can anyone tell me what are the abstract concepts and what are the specific concepts? So I can say that, for example, these are the abstract concepts. I can say this Boolean algebra is an abstract concept, right? I can say this Boolean algebra, this is an abstract concept. Correct? Yes or no? So this Boolean algebra is abstract concept. For example, I can say this is a 4-element Boolean algebra. You know that this is 4-element Boolean algebra. You know this is 2-element Boolean algebra. Okay, this is 1-element Boolean algebra. Similarly, you can create the, okay, you can very similarly you can create the 8-element Boolean algebra also. You can create. So like this. So all of them are Boolean algebra. If you notice, all of them. This Boolean algebra concept you will study in the set theory. So if you did not study set theory, don't worry. Okay, don't worry about it. So this Boolean algebra means Boolean lattice. Yes, this Boolean lattice, this is an abstract concept. Just now we have seen. So this Boolean lattice is abstract concept, right? Correct. So this is the idea. So I can say this Boolean algebra, or the another name of Boolean algebra is Boolean lattice. Another name is Boolean lattice. So this is abstract concept. Okay, these are abstract things. Like if I give you this thing, just think about it. If I give you, like if I give you A, B, C, D, then what is A, what is B, what is C, what is D, right? Yes or no? Agree? So like this A, B, C, D, this is abstract, correct? So this is the idea. So Boolean algebra is abstract concept. And what are the specific concepts? Like I can say propositional logic is a specific concept. This propositional logic. For example, I can say like set theory is a specific concept, and so on. Okay, so these are the specific concepts. Similarly, you can notice this LUB, GLB, like these are abstract concepts. And like this union, intersection, LCM, GCD, this intersection, LCM, GCD, these concepts are specific. Okay, disjunction, conjunction, disjunction. So I can say and, or. So this is the idea. I hope this idea is clear. So what is abstract structure? Is it clear to everyone? Okay, this was our first question, like what is abstract structure? So the abstract structure concept is clear, very simple. So the idea is this, that same structure you can find in many different areas, in many different fields. Okay, this type of structure you can find. For example, let's assume you are a physician, you are a physicist. Okay, so let's assume you are in the physics field. Now in the physics field, let's assume that someday you get a relation in this physics. Let's assume you get some relation, and for that relation, let's assume the hash diagram is like this. Okay, now as soon as you will see this hash diagram, then what will come to your mind? Remember, you are working in physics, your area is physics. Okay, and one day you come across relation, one relation you come across, and for this relation, this is the hash diagram. Then automatically it will come to your mind that okay, so this thing will satisfy all the properties of Boolean algebra. Now you don't have to spend your time. You can immediately say that this will satisfy commutative, distributive, De Morgan, all those properties it will satisfy, right? Yes or no? So that's the idea. So idea is very simple. So the first question is, what is abstract algebra? Abstract algebra is basically study of abstract structures. Okay, and why? Okay, so I can say, what is abstract algebra? If anyone asks you what is abstract algebra, this is a study of abstract structures. This is study of abstract structures. Okay, so in this abstract algebra, we study abstract structures. Because once you study one abstract structure, automatically you can study many different structures you can study. Okay, in future also, if some new structure comes and that structure has the same structure as this, then you can immediately say that, okay, all these properties will be there, right? So that's the benefit of studying abstract structure. Why we want to study abstract structure? Because remember, once you study abstract structure, then you have studied, okay, more than thousands of other structures from many different fields. So that's the benefit of studying abstract structures. Okay, I hope this concept is clear. What is abstract algebra? Now this, remember, what are the applications of abstract algebra? If I ask you, what are the applications of abstract algebra? You know what? Now you know what is abstract algebra. Now you know what is abstract algebra. Abstract algebra is basically study of abstract structures. This you already got. Study of structures. Study of structures, but not specific structures. We will not study specific structure. We will study abstract. We will study abstract structures. Okay, so that's the idea. We will not study, like for example, we will not study this structure 1 2 3 6. Okay, we will not study this structure, but what we will do, we will simply study this structure. This structure we will study, and once we study this structure, then automatically many structures you will have studied. So see, if you don't study this structure, then what will happen? Let's assume you don't study this structure, then what will happen? You will have to study this separately. Okay, you will have to study this separately. You will have to study this separately, right? You will have to study this separately. True, false, a bar. Okay, so this structure also you will have to study separately. So idea is very simple, that instead of studying them separately, what you can do, you can just study them once. So that's the idea. Okay, so this is the concept of abstract algebra. And what are the applications of abstract algebra? The applications are in every field. Let me tell you, in every field of mathematics, in every field, like in the chemistry also. In the chemistry also, this group theory you will study. This abstract algebra you will study in chemistry also. Okay, in physics also you will study this. You are not in physics field, but if you are in physics, then you will also study this group theory. You will also study this. So chemistry people, physics people, cryptography people, computer science people, mathematicians, mathematicians. So whatever name you give, every field, in every field, people will study abstract algebra. Okay, whatever field you take. In chemistry also, people study abstract algebra. Let me tell you, like if you on Google, you just put this word, okay, group theory. On Google, what you do, just put this word group theory, and then just put this word group theory, and then what will happen? If you open 20 articles, then some article will be from chemistry, some will be from physics, some will be from cryptography, some will be from computer science, some will be from mathematics. Okay, so this group theory, if you put, then remember, this group theory is not only a concept in computer science, this is concept in almost all the fields, because I told you, in different fields you can have the same structure. Okay, is it clear? In chemistry also you can find the same structure. Many different things have same structure. So if many different things have same structure, then you just study that structure, right? Yes or no? This abstract structure you study, and then automatically you can study all the different things. For example, in chemistry, let me tell you that most of the viruses, many of the viruses, they have the same structure. Can you notice this virus and this virus? They seems like they look like they have same structure. It looks like, yes or no? This virus, this virus, this virus, it looks like that they have same structure. So actually, let me tell you, in chemistry also, I'm not expert in chemistry, but you can just study about this. In chemistry also, many viruses have same structure. In chemistry, what happens, that many viruses, basically these viruses you can divide in categories. You can divide them in categories. So they can be divided in categories. Based on what? Divided on categories based on their structures. Based on their structures. Okay, so now you can notice that if you study one structure, for example, let's assume you study this structure. Okay, let's assume you study this structure. This structure you study, this abstract structure you study. Now you can notice that in future, if any virus will come which have this structure, then automatically you have, tell me yes or no, then automatically you have the vaccine. For example, let's assume for this structure, this is abstract structure. Let's assume this is abstract structure. Now let's assume for this you have a vaccine. For this structure, let's assume you have a vaccine V. Now in future, after 20 years, after 30 years, if some new virus comes, and that virus maybe, okay, any virus, maybe, okay, COVID virus, whatever virus, if any new virus comes and that has the same structure as this, then what can you do? You can use the same vaccine, right? Yes or no? So that is the reason this abstract algebra is so popular. Okay, so this is in chemistry, this is the application of, this is some idea. I just wanted to give you some idea. So you can use the same vaccine if any virus has this same structure. You don't have to create different vaccine. Okay, so that's the idea. So this is idea of application of abstract algebra in chemistry. So now can you notice that abstract algebra is so powerful? Yes or no? Yes or no? Why this abstract algebra is so powerful? Why this abstract algebra is so powerful? I hope you got the idea. So now you can answer. Remember, if someone asks you what is abstract algebra, if someone asks you what is abstract algebra, then also you can answer it. What is abstract algebra? You can say. So abstract algebra is the study of abstract structures. What is abstract? That also you got to know, right? Yes or no? Abstract versus specific. So this we already know. What is abstract algebra? This is study of abstract structures. Okay, very simple. And now you also know the applications. Some applications of abstract algebra. In every field you have applications of abstract algebra. Let me tell you that once you go to ISC, okay, or in IIT, or okay, so once you go to these colleges for MTech, let's assume, now then you take this course linear algebra. You take this course linear algebra, and let me tell you, the first class will be all about abstract algebra. The first class will be all about abstract algebra. So in the first class you will study group. In the first class you will study group, you will study field, you will study ring. These concepts you will study in the first class. Okay, so once you go to ISC MTech, or maybe IIT Bombay or IIT Delhi, okay, basically some, okay, you go to MTech, you take this linear algebra course. The first class will be about group, field, ring. These concepts you will study, and these are the abstract concepts. Basically these are the abstract concepts, or I can say these are the part of abstract algebra. All of them, they are part of abstract algebra. So abstract algebra is very important. Okay, so we have seen applications of abstract algebra. What is abstract algebra? Now don't have too many questions in this. Okay, this is just a motivation. This is not going to come in the GATE exam. In the GATE exam, they are not going to ask you the definition of abstract algebra. Okay, they will not ask you application of abstract algebra. Don't worry about it. This is just to motivate you. Okay, so the remaining things about it you can study on the internet, because this is not relevant to GATE exam. Okay, if any doubt you have in these things, then you can study on the internet, right? Okay, because these are not related to GATE exam. This is just a motivation. This is just to motivate you to study abstract algebra, like why we study this, what is the reason, what is this, okay, all these things, from where it came. This is the final question. Okay, so we have already seen why we study this. Why study abstract algebra? I told you. This also we have seen, why study abstract algebra. Now the fourth question is, like, when did it start? When did this abstract algebra start? This is the question, and this is actually very interesting question. From where it came, this is interesting actually. This is the reason I want to tell you from where this abstract algebra came. So let's see.